So for a function with two independent variables, when I do what's called partial derivatives, I can do the derivative with respect to x, and I can do the derivative with respect to y. So there are two partial derivatives, one with respect to x, one with respect to y. So I'm going to find both of them. And really the thing you need to know, if I'm doing the partial derivative with respect to x, then y is treated as a constant. And if I'm doing the partial derivative with respect to y, then x is treated as a constant. So the way I would write this, there are several ways to write it. I could write a partial derivative. I could use this, it looks like a backwards 6, and that should be an f. The partial of f with respect to x, and when I took the course, I thought of it sort of as some fancy script sort of D for derivative, but this means partial derivative of f with respect to x. I could also write it f with a lowercase x, and sometimes they'll write the parentheses x comma y. Sometimes they might just write f with a lowercase x. But all of those symbols mean the same thing, and if I'm doing the partial derivative with respect to x, I will say, okay, what's the derivative of x to the fourth? 4x cubed. And then for this, 5xy to the third, I would do the derivative of x, which is 1. And the 5 and the y to the third are constants. And if you wanted to picture that 5x grouped together, the derivative of 5x is 5. But y cubed, that is a constant. So this part is 5y cubed. Because the derivative of x was 1, and when you multiply by 1, well, you get the other, what you started with there, 5y cubed. So there's my partial with respect to x. And then I'll do the partial of f with respect to y. And you could write that as f lowercase y x comma y, or f lowercase y. This time x is a constant. So the derivative of x to the fourth would be 0 because it's a constant. And then plus, now 5x is a constant, so I'll keep the 5x because I have the derivative of y to the third, and that's going to be 3y squared. And if you clean this up a little bit, that's just 15xy squared. And I can do a second derivative. How many second partial derivatives are there for this problem? 4, because I could do the second derivative of this with respect to x, and I could do the second derivative of this with respect to y, and I could do the second derivative of this one with respect to x, and I can do the second derivative of this one with respect to y. So if I take a look at some of the second derivatives, now for second derivative, I'll just write it like this. The second, well, I have to do the first derivative. This would be the partial with respect to x, and then I'm going to go the partial with respect to x again. So I'm going after my answer here. The derivative of this with respect to x will be what? 12x squared, and then the derivative of 5y cubed would be 0 because y is a constant on this part of the problem. I'll put a box around that. How about the partial of f with respect to x and then y? So now I'm looking at this one, this answer from when I did the partial with respect to x, and now I'm going to do the partial with respect to y of this answer. And what's this going to be? This part would be 0. And how about this? 15y squared. Then let's do the partial of f with respect to y, and then y again. So now I'm looking at this answer I got when I did the partial with respect to y the first time, 15xy squared. This time x is a constant, so what would this be? 15x is a constant. 15x times 2y, so that's 30xy. I'll put a box around the whole thing, but here my final answer, 30xy. And then finally, let's do the partial of f with respect to y and then x. So I'm looking at this answer here, 15xy squared, and do the partial with respect to x now. That's going to be, well, x, what's the derivative of x? 1. And then 15y squared, those are treated as constants. So 15y squared. And then I put up yesterday, I did Clairaut's theorem. You can find that in the book, which Clairaut's theorem does say there's some conditions, continuity conditions, but that the partial with respect to x and then y usually equals the partial with respect to y and then x. So I'll put it like this. Notice that that's the case on this problem. Okay, so there's